for volume, let's have a look at one example. And so let's use a triple integral to find the volume of the solid bounded by z equals xy, z equals to 0. Okay, so that's going to be the height of the solid in the z direction. And then what else? 0, x varying from 0 to 2, and y varying between 0 and 3. Alright, so I believe in this case the limits of integration are pretty straightforward, but it's always a good idea to have a look at the projection of the region in the xy plane, in the xy direction, because that's going to help us a lot when it comes to changing the order of the integration, which in this case, well, that's not going to be the case, but it's going to be useful for further exercises, as you will see. So number one, let's draw a Cartesian plane and write down those, or plot these limits of integration for at least for the x and y. So for x, which varies from 0 to 2, and y, which varies from 0 to 3, so we can draw this rectangular box. Alright, so this is our R, our region R. Alright, if you will. So, well, let's not color R, let's just shade it. So 2 and 3, and if we think of this as the base, and well, we would have a solid popping out of the paper, and that solid would be in the form of 2xy. All right, and let's see. So let's write down the triple integral. So volume equals the triple integral over the domain dv. All right. And well, so this will be the triple integral. I'm going to leave some space for the limits. And typically we go about dz, dy, and dx. We go in the backwards alphabetic order, typically. All right? So this is dz, dy, dx. And well, in some cases we may need to change the order of the integration when we don't have like a horizontally simple region or a vertically simple region. Well, in this case it doesn't matter if we do dy and dz and dy dx or dx dy, because it's, if you look at the projection in the xy plane, it's both horizontally simple and vertically simple, so it doesn't matter. But we usually go about what's this? dz, zy, and then x, backwards in the alphabetic order. Well, so x varies from 0 to 2, and y varies from 0 to 3, and z goes from 0 to 2xy. And let's just evaluate this triple integral to find the volume. Alright, so in this case, that's going to be the integral from 0 to 2 times the integral from 0 to 3. And well, the integral of dz, that's just going to be z evaluated from 0 to 2xy. And don't forget the dy dx. And well, in this case, I'm not going to highlight the limits to denote that we are going to plug in only in the z, because that's the only thing we have. We have a z. All right. So that's going to be the integral from 0 to 2, 0 to 3, and well, z upper minus limit, that's just 2xy minus 0, which is just 2xy, dy dx. Okay. And well, so the next step, well, is continue doing the remaining integral. So this time we're going to evaluate the integral with respect to y. So the integral of 2xy with respect to y, this will be, well, the integral from 0 to 2, and that's xy squared, evaluated from 0 to 3, dx. But this time I will highlight the limits just to make sure that we plug them in the correct variable, because in this case, since we integrated with respect to y, we will apply these limits only on the y variable, right? Well, so let's do upper limit minus lower limit. That's the integral from 0 to 2. x times 3 squared minus 0 squared dx. And well, that's the integral of 9x dx from 0 to 2. And the integral of 9x, well, that's just 9x squared over 2 from 0 to 2. And this is simply 9 halves, 2 squared minus 0 squared. And well, that's a 4 divided by 2. That's a 2 times 9, that's 18. So the volume of this solid is 18 units. All right. And again, later we will find out that evaluating this type of integrals is going to take a good minute to solve. You know, so in some cases, or actually in most of the cases for the upcoming exam, for the third exam, which will test you on this chapter, I will just ask you to set up an integral, right? Because I mean, computing that might take forever, and you will be tested on many different ways to set up integrals. I mean, in a double, a triple, double in polar, triple first of all, triple in cylindrical, triple in spherical. So just setting up will be fine. However, I think something like this would be, you know, fair game to compute the whole integral. So at least 1 or 2 exercises on the exam will be computing the whole integral. All right. And let me pause the recording for a second. Oh. Oh yes. Okay, example number 4, set up a triple integral that can be used to find the volume of this ellipsoid given by 9x squared plus y squared plus 9z squared equals to 9. Notice it only says set up. Do not evaluate. All right, well, on the exam I'm going to write set up in parentheses, but do not evaluate, just set up the integral. And well, let's see, what do we have over here? So that's all the information that we have. We have an ellipsoid, all right? They're asking us to find the volume of the ellipsoid. They're not giving us any limits at all, you know, no limits at all. What else? That's all they're giving us. Well, so number 1. Notice if we solve this equation for z, well, okay, let me divide both. Okay, no, let me do one term at a time. So that's going to give us number 1, 9z squared equals 9 minus 9x squared minus y squared, and then z squared equals to, okay, divide both sides by 9. That's 1 minus x squared minus y squared over 9. All right. So that's going to give us 2 surfaces. You know, if this looks a little bit like a sphere. So when we solve for z in this case, that's going to give us a plus minus 1 minus x squared minus y squared over 2. So that plus minus is going to denote the upper half of the ellipsoid, and the minus counterpart is going to denote the lower or the bottom part of the ellipsoid in this case, right? So in a way, we will have to use those symmetry properties in this case to get it, to visualize this region and to simplify our work still. All right. So, but again, whenever we are working on in the 3D space, it's important to see what's going on in the XY. That is, projection in the XY plane. So we need to know what's going on there. So, well, we can take only our positive part. Well, actually, to get this done, let z equals to 0, because that's where we are at the xy plane. When z equals 0, there's no z, there's no height. That's only the xy plane. So if we set in this case, the square root 1 minus x squared minus y squared, and that's not over 2, that's actually over 9. Oh. 1 over 1 minus x squared minus y squared over 9. Set it equal to 0. And it doesn't matter if you put plus or minus, because, okay, I'm going to put the plus minus because we're going to square to get rid of the radical. That plus minus is going to disappear. Alright, so that's 1 minus x squared minus y squared over 9, still equal to 0. And let's get everything on one single side. So I'm going to have all the variable terms on the left hand side and the constant terms on the right hand side. That's going to be x squared minus, or rather plus y squared over 9 equals to 1. And well, this looks a lot like an ellipse. It's an ellipsoid, so it shouldn't be surprising that the projection in the xy plane or any of the traces, remember the traces, the xy trace set equal, that's what we're doing essentially, the xy trace or the yz trace or the xz trace, all right? So that's essentially what we're doing. And well, this is an ellipse where it's actually extending 3 units in the vertical direction and 1 unit in the horizontal direction. So let's draw the graph of that. All right, so that's going to be the following ellipse. So 1 unit in the x direction, 1, 2, 3, 1, 2, 3 in the vertical direction. And that's going to be this ellipse. It's a little slant. All right. So that's our ellipse. That's what we are going to be seeing in the projection in the xy plane, right? So from here we can already get the limits of integration. For example, if we keep arranging this equation of the ellipse, the most natural is to solve for y or x, but usually we go and solve for y, so y squared over 9 equals 1 minus x squared, and y squared equals 9 minus 9x squared, and y equals plus or minus the square root of 9 minus 9x squared, right? So that's so we can see the limits of integration in the y direction. So the plus sign will give us the upper part of the ellipse, while the minus will represent the lower part of the ellipse. So I think from here we can start, we can already define how is everything, what are the bounds in any direction x, y, and z. So number 1, so from this part right here, this is telling us that z is varying between negative square root of 1 minus x squared minus y squared over 9. So that's z. And then in the positive counterpart, all right, so that's z. What about y? Y is varying between plus and minus this radical right here, negative radical 9 minus 9x squared, and 9 minus 9x squared. And what about x? X is varying. If we look at the limits, let me zoom in the ellipse right here a little bit more. So notice how x changes between negative 1 and 1. Are you guys following me up to this point? Yep. So, okay. So x varies between negative 1 and 1. All right. And well, so once we get this, we're ready to just write an integral. And well, that integral will be, it's going to look crazy. And that's going to be the integral from -1 and 1, -1 to 1 in the x direction, double integral from negative root of 9 minus 9x squared to positive root of 9 minus 9x squared, integral of from negative square root of 1 minus x squared minus y squared over 9 to the square root of 9, or rather 1, minus x squared minus y squared over 9. dz, dy, dx. And that's the integral that would give us the volume of the ellipsoid. Do we want to evaluate? No. So do you see what I'm talking about? So only the setup took us, a good minute to go. All right. However, if you may want to rewrite this integral and use a symmetry property, because if you look at the equation of this ellipse, ellipsoid rather, not an ellipse, it's an ellipsoid, there's no shiftings, it's x squared, y squared, z squared, so it has its center at the very origin. So and that makes that shape to be, to be symmetric from any perspective you can think of. Huh?
How did you know x is from -1 to 1?
Oh, that's from the projection in the xy plane. So we got, when we draw these vertical lines to check the vertically simple idea, that's the upper part of the ellipse minus the lower part. In the horizontal direction, that varies between -1 and 1.
So why couldn't you say that y goes between -3 and 3?
If that's a good question. If we reverse the order, instead of writing the integral dz, dy, dx, if we rewrite the integral instead of dz, dy, dx, and we write it dz, dx, dy, then what I did here in green, I would have solved for x instead, and to see the limits in the y direction, and that would have been our integral. And
the first two is a function of the trace, and the last one's always a similar.
Yes. So here the thing is, here when we set up a triple integral, this first variable we integrate with respect to, which in this case is z, is a function of these two remaining variables, x and y. It could be just a function of x, it could be just a function of y, depending on how it's given, or both. And then the next variable, the dy, it's always going to be a function of the remaining variable, in this case a function of x. And lastly, dx, which is the one left at the very end, that's going to be just constants. And so we can rewrite this integral 1 root of 9 minus 9x squared and root of 1 minus x squared minus y squared over 9 dz, dy, dx 0, 0, 0. However, if we take advantage of the symmetry, we can multiply this by 8. Why is that 8? Because basically we're finding the volume only in the first octant where everything is positive. How many octants are there in the 3D space? So we would be finding the volume in over one octant only and multiply by 8 to get the whole volume of the ellipsoid. All right. Questions about this one? All right, let's look at the next example. Let's see what we got. So set up an integral, a triple integral that can be used to determine the volume of the solid bounded below by some cone and above by a sphere. All right. Well, so what is this about? So, okay. So if we look at the sphere, okay, let's start working with the equation of the sphere first. So let's solve for z. So z squared equals 40 minus x squared minus y squared, and z is going to vary between, okay, plus minus the square root of what's this, 40 minus x squared minus y squared. And well, so we will essentially have these counterparts, the upper hemisphere and the lower hemisphere. But again, we may not need both of them, all right? Because in this case, we have a sphere bounded below by a cone, okay? So yes, we have the equation of the cone here. So, okay, number one, let me pause. So from the picture, we can see that z varies is bounded, or it's bounded above by the sphere, by in this case the positive part of the sphere, that is the square root of 40 minus x squared minus y squared, and it's bounded below by the cone, and that cone is the square root of x squared plus y squared. So we got the limits for the z variable. All right, let's have a look at the limits in the y in the y direction and the x direction. However, for those limits, we need to find out what's going on in the xy plane. And in this case, well, notice in this case we have a bounded region by different surfaces in this case. So we need to set the two surfaces equal to each other. So xy plane projection, that's going to be the points of intersection, right, or the intersection. Oh, come on. Intersection. So we need to set the two equations equal to each other. Square root of x squared plus y squared equal to the square root of 40 minus x squared minus y squared. Well, let's solve this equation, or let's try to simplify it by squaring both sides. And that's going to give us x squared plus y squared equals 40 minus x squared plus y squared, or minus y squared. And well, at this point we can move all the variables to the left hand side. That's going to make them x squared, or rather 2x squared plus 2y squared equals to 40. And we can also divide out the coefficients, divide everything by 2. X squared plus y squared equals to 20. Well, so number one, let's list the properties of this equation. What kind of equation is this? X squared plus y squared equals 20. It's a circle. Center at the origin. And the radius is the square root of 20. That is the number whose square is that number 20. All right. Well, so what are we going to have? So it's a circle. If we keep solving for y squared equals 20 minus x squared, and y is going to be plus or minus the square root of 20 minus x squared. All right. And again, the plus minus will represent the upper semicircle, and the minus will represent the lower semicircle. In a very similar than in the previous problem, however, this time we got this projection in the 2D plane, in the xy plane, by setting setting the equations of the two surfaces together, because this time we got two surfaces at the same time, not just one like the ellipsoid. All right, and so I think we got pretty much everything. So, what about the limits of in the x direction? Well, so from here we can write down that y varies between negative square root of 20 minus x squared and positive positive root of 20 minus x squared. And x varies between, well, that's going to be the radius of the circle, isn't it? In this case, negative root of 20 to root of 20. Alright, so we got everything we need to set up our integral. So, triple dv, that's the integral from negative root of 20 to root of 20. Integral negative root of 20 minus x squared, 20 minus x squared, and the integral of, oh my god, square root, oh, be careful here because the lower limit, in accordance with the 3D graph that we saw, which one is the lower limit? Is it going to be the cone or the sphere? The cone. So that's going to be square root of x squared plus y squared to the square root of the upper, well, the part that represents the upper hemisphere rather. 40 minus x squared minus y squared. Alright, and that's dz, dy, dx. And that's the integral that will calculate the volume. Well, we don't want to calculate this volume. And in this case, if we wanted to use the symmetry to have our limits from 0, 0, 0, what would be the coefficient in front of the integral? Careful. It would be 4 because we have a region only above the xy plane. We don't have anything below the xy plane, so it would be times 4. But this, it's fine. If you are asked anything like this on an exam, you don't have to do the symmetry property. This is more than enough. This was already more than enough, right? So, I mean, what I did about the symmetry is just to go a little bit, to go just the extra mile, all right? So, what's next? Set up a triple integral that can be used to determine the volume of the tetrahedron in the first octant bounded by the plane 2x plus 6y plus 3z equals to 12. All right? And the coordinate planes, all right? So be careful with that, the coordinate planes. So this is very important. All right. And in a similar way, we can graph this plane. Let's graph the plane. So we can get the x, the y, and the z intercepts. The x-intercept, set y and z equal to 0, so that's 2x equals to 12. Isn't that a 6? 6, 0, 0. The y-intercept, set the x and the z equal to 0, we were left with 6y equals to 12. That's y equals to 2. And for the z-intercept, set x and y equal to 0. That's going to leave us with 3z equals to 12, which is 4 in the z component of the point. All right. So we're going to plot this plane using the intercepts in this case. And well, unlike spheres or paraboloids or ellipsoids, those are hard to draw. At least planes are okay to draw, so we can do that. So that's okay, 6 units, 1, 2, 3, 4, 5, 6, and then 1, 2, and 1, 2, 3, 4. So that's the plane, right, described by the equation. And notice in this case, it's also bounded by the coordinate planes. That is, the xy plane, the xz plane, and the yz plane. That is, we're going to bound that plane and have 3 walls using this plane right here, the xy plane, and then the bottom right here, which is the xy, and the yz plane. All right, so we're just gonna have a tetrahedron in the end, right? It's not a symmetric tetrahedron, of course. It's just it has different dimensions. All right, let's keep setting up the integral. So that's the picture of the solid. So, and again, we need to know what's going on in the xy plane. So, projection in the xy plane. This will be make z equals to 0, and well, so that's going to be 2x. Well, let's solve for c first of all. 3z equals to 12 minus 2x plus 6y, and z equals to, okay, 12 divided by 3, that's 4 minus 2/3 x plus 2y. All right, and set it equal to 0, so that's 4 minus 2/3 x plus 2y. And in this case, just solve for y to get that function that we will be obtaining in the xy projection. So this is what we're doing essentially. So this,
Should it be negative 2y?
let me check. Yes, has to be negative. Thank you. So negative, yes, and that's an x. So here we're going to take this projection. So this is x, y, and z. This is x, this is y. So it's 2 units in the y direction and 1, 2, 3, 4, 5, 6 in the y direction. All right. So that's what we are seeing from a top view, from the bird's eye view, if you will, in the projection in the xy plane. All right, and well, this will be described by the equation that we are about to solve. So that's going to be 2, let me solve for 2y, so that's 2y equals to 4 minus 2/3 x, and y equals to 2 minus 1/3 x, which is this equation, right? So far so good? Okay, so all this being said, I think from here we can get from the vertical direction. Okay, let's number 1. In the 3D, that is the height of the solid. Z is varying between 0 and that equation that we got over here, 4 minus 2/3 x minus 2y. And what about the next variable, y? So that's where we go, the vertical lines here to determine which one is the top, which one is the bottom. And in this case, the top is the diagonal line, 2 minus 1/3 x, and the lowest point would be another 0 here. And the third variable, x, so we can see that varies between 0 and 6. All right. So I wonder if you notice a pattern here about what we're doing when we're setting up the integral. First of all, we go with the solid surfaces. We solve for the z variable, and then we eliminate one variable to get the traces in the xy plane, that is to see the projection. And then furthermore, we solve for the dependent variable in the xy plane to get the limits in x. All right, so notice how that's the process that we have been following. And ultimately our goal is to gather all these pieces of information, all these inequalities, if you will, because those are ultimately the limits of integration x, y, and z, right? And well, that's the triple integral. The volume will be the triple integral dv in the region. So I wonder if, yeah, that's going to be the integral from 0 to 6, the integral from 0 to 2 minus 1/3 x, and the integral from 0 to 4 minus 2/3 x minus 2y dz dy dx.